This was number 3. So let's just, I'm not going to do every single one, but I'll at least talk about each one. So this one would be a good candidate for the ratio test. And we're basically going to get 1/7. When we do the ratio test on this, you're going to get that the limit is 1/7. So that the limit of the a sub n plus 1 over a n is going to equal 1/7 in this one. So clearly going to converge. And there's no alternating on it. So this is, C wouldn't be a possibility here. It's either going to converge or diverge. So it's either absolutely convergent or divergent. It's going to converge, converge because that ratio is 1/7. And so what happens? So a monomial will always get killed by a exponential term, or like geometric series, right? So this is basically n to the 6th times the geometric series 1/7 to the n, right? In the end, when n gets big, geometric series will always win that battle. Okay, they will always win the battle over a monomial, and that's what we see here in the ratio test. We get 1/7 convergent. Okay, this one. So this one, all you have to do is just look at it and think about it for a little bit, and you can make a quick conclusion. So what is absolute convergence? Absolute convergence is, if we took the absolute value of all these terms, we'd have the sum of 1 over 6 to the n factorial. And so if your brain is on, you look at that and you immediately say, what? Convergent. This is a gigantic denominator, right? So this by itself is geometric with the r of 1/6, and then you're also going to multiply the denominator by n factorial. So these terms get to 0 exceedingly fast, okay? So clearly convergent. You don't even have to, and if you want, you can do comparison to a geometric series. That every term is less than, a lot less than, the terms of the geometric series 1 over 1/6 to the n, okay? Convergent. This one. All right, so it's, this would be a good one for the ratio test, again, good one for the ratio test. I think this will become 1 in the ratio test, so then you're going to get 1/5. Your limit's going to be 1/5. Is that right? No, that's not right. You're going to have n plus 1 over 5. That's not right at all. Okay, so n factorial is gonna win the battle here. N factorial is going to win the battle over 5 to the n. Let's just see that one and play out. So n plus 1 factorial over 5 to the n plus 1 times 5 to the n over n factorial. And so we end up with n plus 1 over 5. N plus 1 factorial over n factorial is n plus 1. You got 1 more 5 in the denominator. So what? So this geometric thing gets crushed by n factorial. This is infinity. Yeah. Because this sequence itself doesn't go to 0. Yeah, totally, absolutely. Because once n is greater than 5, all those ratios, so you can match those all up, right? Because n factorial has n factors. 3, 2, 1. And then how many 5s do we have? N 5s. It's going to be 5. So you can match up a 5 with every factor of factorial and make n ratios. 1/5, 2/5, 3/5, 4/5, 5/5, all the way up. So as n keeps getting bigger and bigger, all these ratios are greater than 1 and getting bigger and bigger. So you're right. So the sequence itself is going to infinity. So by the divergence test. Yeah, good. So yeah, divergence test is fine for that. Is there another question over here? Okay, this one. So this one I think I warned you about. What is 6 to the n minus 1 over 6 to the n plus 1? You just have how many more 6's in the denominator? 2 more 6's in the denominator. So this is negative 1 to the n, just plain 36. And then we have 1 over n to the 1/7. So in terms of convergence or divergence, this 36 will mean nothing. Just a constant times a convergent series will be convergent. A constant times a divergent series will still be divergent. So multiplying by any constant, every term by a constant, will not change whether it converges or diverges. So we're just left with negative 1 to the n over n to the 1/7. That's really what we're looking at. First of all, is that absolutely convergence? If it's absolutely convergent, then we're just looking at what the positive version, 1 over n to the 1/7. Is that convergent or divergent? What kind of series is that? P series. P is less than 1. Divergent. Include the alternating effect, negative 1 to the n over n to the 1/7. So what does that sequence do? Does that sequence, we ask the question, does that sequence decrease to 0? And it does, as long as p is greater than 0, right? As long as p is greater than 0, that sequence decreases to 0. That's the alternating series test. If you have that and you alternate, that's convergent. So this is conditionally convergent. Conditionally convergent. With the alternating effect, it does converge. Without it, it does not converge. It diverges. So that's a conditionally convergent series. Yeah?
Would it be fair to say, or to just use the comparison test and say, all right, 1 over n to the 1/7 is going to be less than 1 over n, and we know that 1 over n is divergent, so.
That's okay. Yeah, that's perfectly okay. It's just more work, right? So you can just identify this as a p series with p less than 1. But that's exactly how we started first talking about p series, just what you said. So yeah, you're absolutely right. Okay, this last one. So now this last one, so in this one we saw that n factorial just crushed it and made it diverge. But look, now you have n plus 2 factorial over n factorial. So how does that simplify? So we can start by just rewriting this as n plus 2, n plus 1 over 7 to the n. So there's really there's no factorial at all here. It's just a polynomial. And that takes us back to this one. And we said that monomial term will get crushed by the geometric. So it's kind of the same. This is kind of the same situation as number 1. N squared plus 3n plus 2. That will get big, but not like 7 to the n will get big. Okay. So if you do the ratio ratio test, the limit will be 7 in the ratio test. 1/7. Sorry, 1/7. But what's happening is that geometric 1/7 to the n is basically what you have. That was, when n gets big, that will totally dominate over any polynomial or monomial. Okay? But it will not dominate over a factorial, right? So this 5 to the n, the factorial will kill that. So that's why that's divergent. Okay, so I'm not showing nice formal proofs here. I'm just talking through them. So you always want to show all the math and give reasoning. Show all the math and give reasoning, which I'm kind of giving verbally. But when you're writing out, if there's written problems or on the exam or homework, you want to write out your reasoning. Any questions on these? Okay, one more. Oh, this one, because it's a radius problem. Okay, so they want the radius of convergence. So let's go ahead and just find the interval of convergence. We'll just do this whole problem. So to get the interval, we're going to do the ratio test. So now we have a power series, which is what? Involves x, right? And we know that these power series are something like a polynomial with an infinite number of terms. Okay, and this one's a little more complicated than just a straight up polynomial. And that's not true. It's just it's got a complicated coefficient, right? So we'll do the ratio test and we'll see what comes. So if the limit then goes to infinity of, so negative 1 to the n plus 1, x minus 19 to the n plus 1, all over 8 to the n plus 1, and then n plus 1 cubed. And then we'll have 8 to the n cubed, negative 1 to the n, and x minus 19 to the n. And so we can pair all these things up, right? So negative 1 to the n plus 1 over negative 1 to the n will just be negative 1. There'll be 1 negative 1 in the numerator, but then we're going to take the absolute value. So a negative 1 to the n, when you do the ratio test, it just goes away. Now, if it's something other than 1, then we don't want to. If it's negative 7 or negative 5, then that will give you, that factor of 5 or 7 or whatever it is. So, but since it's negative 1, all we get is negative 1 on the top and the bottom. We take the absolute value, it's gone. Okay. So then we've got x minus 19 to the n plus 1 over x minus 19. So we have one more x minus 19 in the numerator. 8 to the n over 8 to the n plus 1. One more 8 in the denominator. And then we have the n cubed over n plus 1 quantity cubed. So we can imagine multiplying that out. What would the leading term be? The leading term of the denominator? N cubed. So we'll have n cubes, essentially n cubed over n cubed. So that will go to 1. Okay, so what do we need? We need this thing, x minus 19 over 8, absolute value of x minus 19 over 8, to be less than 1. If it equals 1, no conclusion. We have to do those cases separately, right? Those will be our endpoints. But so we're going to say that x minus 19 then, if the absolute value is less than 1, then that value has to be between negative 1 and 1, which means that x minus 19 has to be between 8 and negative 8, and x has to be less than 27 and greater than 21, 11, 11. Okay, and so that's our initial interval. But remember, so if x is 27 or 11, that's what's going to give us plus or minus 1 in this ratio. So if it's 27 is going to give us 1. 11 is going to give us negative 1. So that then the ratio test can't give us any information about those endpoints, right? So we got to do those separately if we want to get this this full interval. So we'll put in 27 into here. When we put 27 in, what do we get? 8 to the n. Is that right? So putting 27 in for x. This whole thing will be 8 to the n, and then that will go away. And we'll have negative 1 to the n over n cubed. Convergent or divergent? Absolutely convergent or conditionally convergent? Because p series with p greater than 1. Okay, so this would, the result, when you put in x equals 27, you get a alternating p series that's absolutely convergent because p is greater than 1. So what do we want to do with 27 here? Include it. 27 gives us convergence. Okay, when we put 11 in, what do we get? We get negative 8 to the n. So let's do the math here. So when we're going to put 11 in, so we can see how the minuses work out. When you put 11 in, you get negative 1 to the n, negative 8 to the n, over 8 to the n cubed. So what is negative 8 to the n over 8 to the n? Another negative 1 to the n. And what is negative 1 to the n times negative 1 to the n? Right, so either those are going to be both positive or both negative, right? For any given value of n, it'd both be negative or both be positive. And so then that's just 1. So when you put in, when you put in 11, all the alternating effect cancels out. And all you have left is 1 over n cubed. It's not alternating. Convergent or divergent? Still convergent. It's still a convergent p-series, right? So we're going to include both. So our interval is going to include both 11 and 27 because it's convergent on both ends. And then our radius is half the distance across here. 8. So radius would be from the center. The center would be at 19. So from the center out to the edge, like think of a circle, right? Think of a circle. From the center of this interval is 19. The distance out to the edge or out to the endpoints is 8. That's our radius. Question, John?
Let's say hypothetically it was just negative 1 to the n over n cubed.
Uh-huh.
Since that would be absolutely convergent, wouldn't this still be included? Wouldn't the point still be included?
That's exactly what happened when we did 27. So when we put 27 in, that's what we got. We got negative 1 to the n over n cubed.
Okay.
Yeah, and whether in this case, for the interval of convergence, it doesn't matter if it's conditionally convergent or absolutely convergent. You want to include it because it's convergent. But yeah, that's exactly what happened when we put the 27 in. We got the alternating p-series with p equals 3. So yeah, so in both cases, convergent. Did that answer it? Questions on this example? So all they wanted was 8, but you're definitely responsible for coming up with an interval like on this one, like we did. Okay, and so maybe in recitation, if you have recitation today, you'll do a few more of these. Last chance, questions on the homework. Okay, so let's press on. So we're in these power series now. We're in the realm of what? That the series are kind of representing functions. These series are representing functions. A power series is kind of like an infinite polynomial. Okay. Well, what about the other way around? What if you started with a function? Could we create a series to represent that function? So rather than starting with a power series and saying, oh, look, it's kind of like a function. What if you started with a function and said, could we write a series to represent that function? So that's the next topic. And this is pretty cool stuff. Hope you like it. Okay, so we want to represent functions with power series, and this is where it all begins. It begins with geometric series. Okay? Remember, we got the form of the geometric series when you're starting from 0. So when we introduced it, we started from n equals 1. And our exponent was n minus 1, and then we talked about shifting the index, right? We shifted the index back from 1, starting from 1 to starting from 0. And then in order to get the same terms, then we had to crank up the exponent in the term so that we end up getting the same terms, right? So we did that last time. And we know that when r is in the radius of convergence between negative 1 and 1, that geometric series is a over 1 minus r. So we're going to use this, and we're going to start with looking at functions that kind of look like this. Right? It's a very narrow class of functions, but it's a place to start, and we can actually get lots of functions to look like that. Okay, but it's still pretty narrow, but it's a good place to start, and it ends up being helpful in lots of cases. All right, so we're going to look at the function 1 over 1 minus x. So if you recognize 1 over 1 minus x, what that's kind of like, you could write it as a series. See if you recognize what you're looking at and see if you can do it. Can you write that as a series? Okay, anyone figure out how this kind of works? You see it? Corey?
The summation from n equals 0 to infinity of x to the n.
Okay, so you jumped over a lot of stuff there, but yes, you probably got it. But we're going to take it one step at a time. So what do you see?
I had the same thing, but yeah, just a would be 1, and then r would be x.
Okay.
So it would just be x to the n.
All right, that's what you're thinking too. Okay, good. So it looks like you should see that it looks just like a over 1 minus r. So then a would be 1 and r would be x. And so then we can just take our a, take the 1 and the x, and we can write this, which is exactly what Corey said. All right, so then 1 over 1 minus x is summation a r to the n, which now is 1x to the n. And so what is that? We know that what that is. When we see this right here, we think this. When n equals 0, we get 1. When n equals 1, we get x. When n equals 2, we get x squared. And then we're just going to add those up, right? Forever. Now, but this is only, this relationship, this function can be written as the sum only for the convergence, right? So only between -1 and 1, when x is in the interval -1 to 1. So you imagine if x was greater than 1 or less than -1, what would this thing do? So if, like, say, if x was 2, it's just going to get huge, right? So it's just going to whirl off, right? So, but if x is between -1 and 1, and you've got all those multiplied by itself, right? Then you're going to have contained values, right? They're going to be contained. They're not going to whirl off because they're going to keep getting smaller as you multiply them by each other. Okay? And so then when you add these up, if you're able to add up all infinitely many terms, then between -1 and 1, you get the same function as this. So let's see this in action. So does that make sense? Any questions? Okay, so here's that function, and I've graphed it between -1 and 1. So this is 1 over 1 minus x between -1 and 1. And then I'm going to look at, so we found that it's basically x to the n, right? X to the n. So let's look at partial sums, right? So whatever the sequence of partial sums does, that's the same thing that the series does. Remember that? The sequence of partial sums is where you just keep adding one more term to the one before and you make a sequence out of that. So this capital N is going to be, so I'm going to be able to adjust that capital N down here. So when n equals 0, what do we get? If n is just 0, then what do I get for my series? It's just 1, right? So this is just the first term of that series, just the 1. Okay, so here's how it is replicating the actual function 1 over 1 minus x. Okay, now I'm going to look at the next partial sum, which would be 1 plus what? 1 plus x. Here's 1 plus x. So how did it just get better? So now how is this doing a better job replicating the actual blue function 1 over 1 minus x? See what it has that the last one didn't? So that's just 1 and 1 plus x. Right, so that would be what about 1 minus x that's correct? That's 0. So now that 1 plus x, what is correct about it at 0 relative to 1 over 1 minus x? Yeah, and what is that? Yeah, so the rate of change of the derivative, right? So the rate of change of the derivative at 0 is now correct. And you see that right around 0, it's pretty close. If I add another term, so 1 plus x squared. Now it's curved, right? So the red one is what this is right here. It's our partial sum for n equals 2. And it's curved, it's hovering. So now around 0, it's doing a really good job. And then each time you add one, each time you add another term to that sequence, it replicates what's happening around 0 even better, but then away from 0, it's getting better and better. Do you see that? So here's the first, 5 terms. So the more terms that you add, the better and better that power series, x to the n, is going to reproduce the original function in the interval from -1 to 1. It kind of works its way out, right? It's really good around 0, and then further and further away from 0, it keeps getting better and better. So I have it all the way up to 10 here. And in this view, those are pretty dang close. By the time you get to the first n equals 10 is the first 11 terms. So you can see how this works. But now outside of -1 to 1, it will blow up, right? If we were to graph it, so let's take away the -1 to 1, and you'll see that outside -1 to 1, it will not match the blue one at all. So less than -1, our estimate goes up to positive infinity. The actual function is asymptotic to 0, and then greater than 1, the red function is nowhere to be seen. It's huge, and the blue function, the 1 over 1 minus x, is actually negative. So you see how it's converging between -1 and 1. Yeah, John.
I don't think I understand the significance of the partial sums. I should
I should have called on you earlier. Okay, so the first partial sum. So what is this thing? It is wrong. We said that this can be approximated by the series 1 plus x squared plus x cubed plus ... So what I was showing you was we were looking at partial sums, right? The first partial sum is just 1. The next partial sum is 1 plus x. The next partial sum of this is 1 plus x squared. So these are all estimates of 1 over 1 minus x. If you could write all infinitely many terms of this, then you would get the function 1 over 1 minus x between -1 and 1. So what I was showing you was that each partial sum does a better and better and better job of reproducing this. So here I'm showing you just 1, right? The first term of the series, just 1. That looks like that function right there, just the horizontal line 1. So that's correct. The only thing that's correct there is the function value at 0. It's just at 0 you get 1. But if I do 1 plus x, not only do I get the function value at 0, but also the first derivative. The rate of change is correct. And it's pretty close, right around 0, but then away from 0, it's far away. So now this is now 1 plus x squared. The first 3 terms of the series is doing a really good job around 0, and we're getting more accuracy away from 0. And each time we add another term, the power series, the partial sum of the power series does a better job of reproducing the 1 over 1 minus x. So then all the way up to the first 11 terms would be n equals 10. We can almost not see the difference unless we get really close to -1, and then there's still some difference there. But it's very close. Is it better? Okay. Yeah. Ask me again now. Right, of the series. Yeah, so the sequence must go to 0 in order for the series to have a chance to converge. And the series will add to a non-zero number if it does converge. So when a sequence goes to 0, then the series has a chance to converge. And when it converges, it'll converge to something that's not 0. Yeah, so the series and the sequence are totally different. But the sequence of partial sums, the limit of the sequence of partial sums is equal to the sum of the series. Because you're doing what I'm doing right here. You're just looking at a list of values that are each one is adding another term of the series. So the further you get down that list, the more terms you have and the closer you're getting to the sum of the series. Is that help? Yeah. Other questions? Okay. So yes, okay. So let's do this one. Represent, write x over 2x squared plus 1 as a power series and find the interval of convergence. Okay, so what do we know? We know that we can do it if it's in the form of what? A over 1 minus r. So can we get this to look like a over 1 minus r? So here's some keys to this. This has to be a 1. It can't be any other number. It's got to be a 1. So are we okay in that regard? So we can write this as x over what? 1. And then we want minus what though? It's 1 plus. So what could I say? Minus 1 minus what is the same as 1 plus 2x squared? Minus negative 2x squared. So do you see how that's exactly equal to g? That's the same as function g, but it's in the form of a over 1 minus r. So our a is x, and our r is negative 2x squared. And so we can do it. So we want to write that power series, and then let's just simplify it. Let's just go that far. Don't do the ratio test yet. So we're all on the same page before we start the ratio test. So set up the series, simplify the general term, right? So simplify what you get. Zach, did you get it?
I think so.
Tell me.
I have, so a is equal to x
Mhm.
and r is equal to negative 2x squared.
Mhm.
Your unsimplified is going to be x times negative 2x squared to the n. Then I kind of got a little mixed up.
Okay.
And I thought that maybe you could put the x with the 2x, negative 2x squared, so you could get, you multiply by another x.
Okay.
But I guess that's either 2x or negative 2x to the third.
Okay. So right. So we want to apply this power of n inside and combine because we got an x out here and more x's in here. So first of all, we get the negative 2. So being that would be negative 2 to the n, right? Negative 2 to the n. And then in here we have x. What's the power of x here when we combine everything together? X to the what? 2n. So we have x to the 2n. And then we have how many more x's? Times one more x. So what would that exponent be if we have x to the 2n and then one more x? 2n plus 1. Did you catch it? Does it make sense? Or did I lose you? So what is this? So it'd be, this is x times negative 2 to the n times x to the 2n. Do you see that? Because the n, yeah, so the n negative 2 to the n and x to the 2n. Well, what does this mean? It means take 2n x's and multiply them together, but then there's one more x. So how many total x's are we multiplying together? 2n and one more. 2n and one more. X's multiplied together. Is it better? Yeah, so we're gonna you're gonna need to know how to simplify these because yeah, when problems get harder and we're doing other things, you're gonna want a simplified form. So and you gotta know your laws of exponents. So we're gonna do that. Okay, so now we're ready to find the interval convergence. So now we just have a power series, right? And we're gonna do the ratio test. So it's gonna be limit as infinity of. So someone want to help me out here? I'm gonna do the ratio test on this. Is it John? Tell me, John.
So it'd be negative 2 to the n plus 1
Uh huh.
times x to the 2 parentheses n plus 1
Uh huh.
plus another 1
Right.
divided by just this
That thing.
2 to the n.
Yeah. So since we don't have a fraction to start with, we can just start with a fraction. That's gonna be the easiest thing to do here. Okay, very good. Simplifies to. So how does this simplify? Negative 2. And then how does this simplify? So x squared, right? Okay, so this is a little, and we need this thing for convergence to be less than 1. So there's no n's in here. This doesn't care what n does, right? So the limit as n goes to infinity is just this. Okay, so we got to think through this a little bit. We need negative 2x squared to be the absolute value of that to be less than 1. What is the absolute value of negative 2x squared? Just 2x squared, right? Therefore, x squared has to be less than 1/2. Okay, so now we got to think about this. So x squared has to be less than 1/2. So certainly x needs to be less than radical 2 over 2, right? Or square root of 1/2. Then we got to think about what's going on with x squared, right? What's the lower limit of x? Is it 0? Yeah, so you can, right, so we want all the negative numbers that have a magnitude less than 1 over radical 2 as well, because when you square it, it'll still be less than 1/2. So we need the lower limit of x to be -1 over square root of 2. So that when you square it, you could square any of those negative numbers in there, and it'll still be less than 1/2. Did you catch it? Make sense? So now the question is, what about the endpoints, right? So we've got the basic interval, but we've got to check our endpoints of plus or minus 1 over square root of 2. So we go back up to original series right here. So we could use, we could use this version right here. So we're going to check plus 1 over square root of 2. And what do we get? We get n equals 0 to infinity of -2 to the n times 1 over square root of 2 to the 2n plus 1. So what is that? Okay. So we're going to have to, now we're going to have to kind of work backwards the way we came from to actually make some sense of what that number is. This one here? Yeah, because that's where we're going. So let's just start with that, right? So you're exactly right, and that's where I was going to go. So let's just go back. Let's just use this first one in order to evaluate it. It'll be easier, right? So 1 over square root of 2 times -2, and then what is this thing squared? 1/2, right? Yeah, much easier. Okay, much better. So what do we get? N equals 0, infinity, 1 over square root of 2 times -1 to the n. Convergent or divergent, and why? Convergent or divergent, and why? 1 over square root of 2 times -1 to the n. What's that? Conditionally convergent. What do you think? Agree with that? Who's saying no? Because of what? There's no such thing. Yeah, there you go. Yeah, so what about this sequence? What is the sequence? This sequence is -1 over radical 2, 1 over radical 2. -1 over radical 2, 1 over radical 2. How about that sequence? Divergent sequence. Game over, right? So what does the sequence have to do in order for this to have a chance to converge? They all said? Go to 0, right? Your sequence must converge to 0, and then there's a chance the series can converge. This is a divergent sequence, so this could never converge. Divergent by the divergence test. Divergence test looks at the sequence. If that sequence doesn't go to 0, game over. It's divergent. All right, what about negative? When we do negative, we get the same thing but with 1 to the n. Right? When you check -1 over radical 2, oh no, you still get the alternating thing. So you're going to have -2 times that thing squared, but this will be negative. So when it's n equals 0, you get -1 over radical 2, but you still get -1 to the n. Conclusion? That one also divergent by the divergence test. So it's only convergent strictly in the open interval. The endpoints, it's not convergent. So between -1 over radical 2 and 1 over radical 2, this series will reproduce this function. And the more, so if you look at partial sums, the more terms you take, the better it will do at reproducing that function. If you could somehow take all infinitely many terms, you would get the function g in that interval. Question?
If we were to put the graphs on top of each other, because it doesn't converge at the endpoints, would there be like some sort of asymptote looking thing?
So yeah, so we could try it if you want to try it. I could fire that up and we could do it in here. But yes, so it will never. It will get closer and closer, but it will never reproduce it at those endpoints. So maybe yes, so maybe some kind of asymptotes. But we should do it. Okay.